All right, let's go ahead and get started. So announcements. No new hand-in homework for this Thursday or for next Thursday. Instead, you can keep doing your review to prepare for the test tomorrow. There's some online homework due next Friday on the 8th, so not this Friday. Test is at 6 to 7:30 p.m. Bring your calculator, bring a pencil. Question? Oh yeah, no class on Friday, so yeah. Yeah, bring your pencil, bring your calculator, and you should bring some kind of an ID as well, just like the first exam, so that we could see that. Preparations. So there's ordinary office hours, and then there's also the reviews session recording is on Moodle. I put that up this morning. There's a study jam tonight, 6:30 to 9 p.m. in Wilmington. You should check that out. And then the Thursday lab is also for review purposes. So you could go to any lab or none of them or 3 of them and review during that time. The first lab is at 8 a.m. The last lab is at 3 p.m., 3 to 4 p.m. And they're all in the same room on Thursday. All right. Any questions with any of that? All right, so I thought that we should start today with a little bit of like a couple of review problems. So the first review problem, let's do one on an experiment. I was wondering if someone had a favorite animal. Does anybody have a favorite animal? A bear? I heard a bear. You said bear. I heard bear. Bear. Let's just do it on a bear then. So let's say our experiment is on sleep deprivation and aggressiveness. So explanatory variable would be sleep deprivation. And the response variable would be aggressiveness. We could also maybe throw in another factor. How about hungry? Yeah, if you're hungry, you're aggressive. So yeah, hunger level as well. Okay, so we've got the factors. Could be calorie intake, that day. And then we could also have hours of sleep the previous night. And then let's have like an aggressive rating. It would be kind of a hard thing to test for sure, but let's just say like you try to walk towards it and you see how far away you are before it tries to like growl at you. Roar at you, I guess bears roar. All right. So that would be the response variable. Distance to roar. All right, so we want to be able to draw a diagram of this. So let's start off with the bears. So we got some bears. And then we have, let's do hours sleep first. Maybe kind of make things a little different. Let's do 4 levels. So let's say we have 0 hours, 3 hours, 6 hours, 9 hours. And then let's have a calorie intake. Well, I'm running out of room, so let's just do 2. So let's say nothing, and then 4,000 calories. I don't know how much do you think bears eat? 5,000 calories? Sure, 5,000 calories. So 0 calories, 5,000 calories. 0, 5,000 calories. 0, it's 5,000. 0, 5,000. And then at the end, we compare all of these. Okay, so we're out. So we compare aggressive ratings, aggressive, sure, rating. All right, so we're forgetting one thing here. We need to do some random assignment. So don't forget about that. It's easy to forget. So we got random assignment here. And then we've got random assignment here as well. Okay, so let's say we have, if we had 120 bears. That would be kind of tough. But let's say we had a lot of money for our grant and we were able to find 120 bears somehow. That would mean that there would be 30 bears in each of these. 30 bears, 30 bears, 30 bears. And then we'd have 15 bears in each of these guys. 15, 15, 15, 15, 15, 15 bears in all of those, all right? All right, so let's say what the factors are. So how many factors are there? 2, all right. How many levels in the hours of sleep factor? 4. So we count them, 1, 2, 3, 4. How many levels in the calorie intake factor? 8, 2, some other number? So 8's too many. So there's 2 levels. You can either have 0 or 5,000. And all of these are repeats, so they don't actually count as another level, right? So maybe I should write that down. So 2 factors. Calorie intake has 4 levels. Hours slept has 2 levels. Oh, I switched them around. All right, 2 and then 4. Yep, good call. Calorie intake has 4. Hours slept has. Calorie intake has 2. That's what I mean. Yes. Just look at the page here. Question? Oh, yeah. It'd still be the same thing. Yeah, yeah. So the end result will be 8, 1, 2, 3, 4, 5, 6, 7, 8 groups there. Yeah, yeah. So it's just written differently. But yeah, it would be exactly the same thing. So, right. So treatments. How many treatments are there? This is the. Well, I'll let you say it. How many treatments are there? 8. Yeah, this one's the 8 one. So you could go 1, 2, 3, 4, 5, 6, 7, 8. 8 ways to get to the end. All right, so we got factors, treatments, experimental units are the bears. What else? Could we replicate this? Yeah, we could get other bears and replicate that. We're comparing, so there's some kind of comparison going on there. Is there control? We would like to hope so. So we would want to have the conditions be the same for the bear, other than so like the same pen or the same cave. I don't know, wherever you stick the bears to do the test at. You wouldn't want to have different areas for the tests that you're testing the aggressive rating. Yeah. You could control for weather too. Just make sure that you do them all on the same day. All right. And then like maybe the same time of the day as well in this case. All right, so there's that one. Let's do a sampling method review problem. So could someone name their favorite plant and raise your hand? Favorite plant? Blueberry bush. All right, so we're going to do a sampling method on a blueberry bush, blueberry bushes. So this was a sampling method. Maybe I'll draw a picture. I don't even know what a blueberry bush looks like. Does it look like a normal bush, but just with blueberries? What does it look like? Can I just Google it? Okay. I hope it's a nice search. All right. Sometimes you never know, huh? What? Mm-hmm. Oh. So normally what happens is I give you like a little bit of a setup, like we're doing some kind of a study on bears. Yeah, so there'll be like some kind of a setup for that, and then you have to decide is it an experiment or is it an observational study, and then then you may have to draw a diagram. Well, you will have to draw a diagram for one of the questions. So like that with the random assignment and the compare the results at the end. Yeah, but you need to know like about all the things with the experiment, like what the factors, the levels, experimental units. If there's a placebo or if it's blind or double blind, you have to know that kind of stuff. Okay, so let's see what blueberry bush looks like. Bush. All right, that's cool. Oh no, it's not a picture. There it is. It's $29.95. Act fast. All right, so it's got a lot of blueberries on it. I'm surprised. So let's um, say we have oh, let's go back to the other one. So let's say we have a garden of blueberry bushes. Oh, I wish I had a blue pen. No. So we got a bunch of little berries here. And let's say we've got them in a nice grid format. Just because we're producing blueberries at scale. All right, so we got our little picture here. Yeah, it looks exactly the same as on the right as on the left. Exactly the same. All right, so let's say that we numbered all of these 1, 2. Say we have some down here as well. So numbered 1 to 100. Yeah. Let's get rid of the bush. Huh? Yeah, it is a very nice. Yeah, it is a very nice plant. So numbered 1 to 100. So you could use random.org and just pick out some. Say you wanted to pick out 10 of these bushes to maybe count how many berries they have on them, or weigh them or something. Yeah, you could weigh them, see how large they are. So you could use random.org and pick out just pick out like 5. I guess I could write it up here, but, to pick 5. All right, so now we have to decide what kind of sampling method this is. Any ideas? Or there's a question first. So each garden plot is a bush. So I wanted these to be like planters, and then have like one bush in each of them. We could, yeah. So yeah, we could make each of them a garden plot as well, but let's save that for stratified sampling. Question? No question. All right. Does anybody have an idea what, like, if you just randomly picked 5 from all of them, what that'd be? It's SRS, yeah, SRS. Yeah, so it's a simple random sample. We're picking 5 from everything. So that's SRS right there. And then let's say that we picked every fifth bush. What kind of sampling method would that be? Any ideas? Systematic, right? Right. So there's some kind of a list here. So you could list these off and just go left to right like you're reading. So every 5th one, 1, 2, 3, 4, 5th, that one, 4, 5, that one. Yeah, the problem here is that you're only ending up on the last row. So that is an issue with systematic sampling, is you may get into one strata when you didn't even realize it, and you may get biased there. Stratified. So pick. Well, I gave the answer away, but pick. Here. I'm going to change it. Throw 2 nets randomly into your garden. and then and sample all of the bushes you catch. So what kind of a sampling method would that be? Oh, I had it down again. Sorry. So you're just maybe you're blindfolded and you throw some nets out into your garden, and then you catch some. You have some bushes underneath the nets, or maybe hula hoops would be a little better. You could throw some hula hoops out in your garden and see what bushes you have within those hula hoops. Yeah, any ideas with that? Cluster, yeah. So you're getting a cluster of bushes together, and then you're doing a census within those randomly picked clusters, so to speak. So I guess I could write this. So systematic. This one's cluster sampling. And then let's think of a stratified one. So let's say you pick one randomly from each row. So pick one randomly, one bush. Each row. All right. That one is stratified. So that's maybe if you think that that maybe the east side is a little growing a little better than the west side, or maybe there's some shade, a little more shade on one side of all your blueberry bushes. All right. All right. Any questions with those? Would anybody like me to do a probability one as well to cap it off? All right. So let's. So instead of marbles. Oh, we got a question in the back. Yeah, so you can do cluster sampling is when you do a census within each cluster, but then you could also do a multi-stage where you do cluster and then you'd sample within the cluster, do like an SRS within each cluster, and that would be a multi-stage. Does that make sense? Random cluster sampling. So cluster sampling is already random. So you pick the clusters randomly, but then within each of the clusters, it's not random because you're looking at everybody in that cluster. So if you say random cluster sampling, you're just adding an extra word for no reason, that random word. What's someone's favorite chance game? Someone else? Did someone say something? Someone else. Someone else. Yahtzee? I think, was that? Yeah, because you did the Bears one, right? Yeah. Yahtzee? I like Yahtzee. Yahtzee. So what are the chances of getting a Yahtzee? Right? So remind me. So Yahtzee is with a 6-sided die, right? And then a Yahtzee means that you get 5 of a kind, right? You're right. You get a Yahtzee. So so 5 dice, all of the same number. Is a Yahtzee. So what are the chances? Well, let's probability of Yahtzee equals what? What is that? All right, so we could get Yahtzee with 1s, with 2s, with 3s, with 4s, with 5s, with 6s. And each of those are disjoint. So you couldn't get a Yahtzee with both 1s and 2s at the same time, because then neither one of them would be a Yahtzee. I don't know. It's just impossible. So you have all 1s or either all 2s. You can't have 1s and 2s at the same time. All right. So we've got 6 disjoint events there, and we could add them together because they're disjoint. And then each die is independent from the other ones. So those ones you can multiply together. All right, so we're kind of getting an idea here. So let's find the probability of all 1s on your die. So that's the same as the probability of, well, let's say that we have, let's call it die, or maybe O1. And O2 and O3 and O5. So let's say that O1 is equal to first die is 1. O2 is equal to first die, or second die is equal to is 1. All right, and so forth until O5. So fifth die is 1. All right, so those are what those events are. And so we want to find the probability that all 5 of those dies are 1. So first, second, third, fourth, fifth. So we use the multiplication rule here. Times, so the n becomes a times. These are independent events right there. And the probability of getting a 1 on the first die is 1 out of 6, right? Because there's 6 sides, and you've got 1 chance to get a 1. So we've got 1 out of 6 times 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 1 out of 6, which is 1 over 6 to the 5th, or 1 over, yeah. So to figure out what that is, I got 0.00013. So what I got. All right, and then we also want to know what the probability of all 2s are, what that equals. And we can think about this, and we can say, oh, okay, this is looking really familiar to what we just did. So again, it's 1 out of 6 for each of those, for getting a 2 for each of those dice. Yeah. So it's going to be the same thing. So I feel pretty comfortable just writing that because it's the same thing. Question?
Are those 3 all the same? Like how you wrote the one and those 2, like, yeah, those 2 lines all the same?
Yep, they're all equal to each other.
Okay. Could you maybe elaborate on the terminology of disjointed versus independent?
Oh, okay, yeah. So independent means that that one event does not affect the other event. So rolling 1 die does not affect the probabilities of your second die. They're completely independent from each other. And then disjoint means that 2 things can't happen at the same time. So you can't both get a 1 and a 2 at the same time. So like rolling a single die, you can't get both a 1 and a 2 at the same time. So so we're getting there. We're gonna add all at the end here. So we'll add maybe at the bottom of the page, just where we're heading. All 1s plus probability of all 2s plus ... probability of all 6s. Right there. So that's we can't get the 1s and 2s at the same time. So those are disjoint. Okay. Yeah, it's a two-parter. So you have to realize that Yahtzees, you can split them into Yahtzees of 1s, 2s, 3s, 4s, 5s, and 6s. And then you have to find each of those individually as your second level. Yeah, I wouldn't call it a disjointed probability, but I would call it a adding up the probabilities of the disjoint events there. So, yeah. All right. So yeah, this is where we're heading down at the end. Any questions with that? All right. So we're pretty much there actually, because the rest of these are also the same, because it's 1 out of 6 for each of those individual die. Probability of all 6s is 0.00013. So they're all 0.0013. So now we have that on the bottom here, 0013. And we ended up with 6 of those, so it's like 6 times that. And now this is the big payoff here. 6 times 0.0013 is 0.00078. Or you could say it's equal to 0.078%. So about 1/10%. So that means that if you roll 1,000 times would be about when you would expect to get a Yahtzee. So, all right. Any questions with that problem? Yeah, one more.
Where did you get the 1/6?
Oh, yeah, the 1/6. Like up here? Right, so the 6-sided die corresponds to the 6 in the denominator. And then the 1 stands for how many faces that you could get. So we're only interested in one face, the face with the 1 on it. So that's why we have a 1 up here. So it's a 1 out of 6 times you would get the 1 side of the die. So, right. Oh, 6. Right. Yeah, only 5 die. But then there's 6 numbers. So yeah, that's why there's 5 of these, and then there's 6 of these down here on the bottom. So, all right. So let's go back to confidence intervals. Get through a couple more pages here, so we can get back to that. All right. So what page are we on? We're on page 196. So we have to use the central limit theorem for confidence intervals as well. Remember that picture I drew with the, there was a normal distribution. And then also remember that the standard error uses the central limit theorem. So maybe I could just write what the standard error is again. Standard error of p hat is equal to the square root of p hat times q hat over n. So that uses the central limit theorem right there. And then let's just write what the that formula is again. So the confidence interval, well, yeah, let's just write the expression actually. So p hat plus or minus z star times standard error is what it was. Z star was the critical value, and that depends on what our confidence level is. So how wide of a interval do we want? And then the standard error depends on, so it has n in the formula for standard error, depends on the sample size, and then it also depends on a little bit with what your p hats and q hat are. So, all right, so it's the same independence assumption here. So we've got a SRS, we've got the 10% condition, and then we also do the success failure condition as well. But the only difference here is that we can use p hat. We can use p hat and q hat right there. Because we're estimating p, because we don't actually know p right now. So. All right, so let's look at here what is a confidence interval. So what does it mean when we say we are 95% confident? So what that means is that 95% of samples that are chosen in the same way, of the same size, 95% of those will contain P. All right. So yeah, let's read down here for a little bit of a more maybe grounded example here. A little more. Yeah, so let's say the true proportion of US adults who had a cold was 8% yesterday. And then we take random samples of size 1,000 from the population of all adults. If we did it 100 times, if we used a 95% confidence level, that would mean that 95 times we would expect to get 0.08, get that p-value within the interval. All right. And we've got a nice picture over here. So gaze upon this here. So each of those little lines is a confidence interval. So intervals are some kind of a length. And if you kind of scan down here, so this one captures P. So P was 0.08. But then you get one right here. That guy did not capture the P, the true proportion. If you go down here, some of them are kind of close, like this one's kind of close to the edge. And then there's another one right there, another one. And I think this one just barely missed it. Right there. All right, so this happened 1, 2, 3, 4 times. So it doesn't have to be exactly 5%. This is like probability. In the long run, it will be exactly it'll approach exactly 5% of these not containing the true proportion. All right, so I'm just gonna let this sink in a little bit because this is like a really awesome way of understanding what confidence level means. So, and this is where your confidence comes from. It's because you have a confidence in a probabilistic sense. So you could be wrong, but you're probably not because you have that confidence. Chances are that you actually do know where that true proportion is. So the sense here is that if it's high stakes, if it's really, really important that you actually know, that you actually have that P, you would want a higher confidence level. So if there's, like, let's say there's a 5% chance that, that you break your leg, you would not want a 5% chance of that. So you would want a higher confidence level to avoid serious injury with something like that. Or like with medical procedures or things like that, you would want a really high confidence level. All right. So this was with colds. So it's not high stakes, so to speak. It's just it's good to know to keep tabs on trends. What are some trends that are occurring? But it's not like someone's gonna break their leg if you don't know exactly what proportion of people had colds yesterday. So not high stakes here. All right, so let's get through this example here. So, all right, so we've got a Pew Research Center, 1,502 U.S. adults, 69% said that they do not want to see the Supreme Court overturn its Roe versus Wade decision in 1973. So now we're getting controversial here. So I hope that's exciting for you. All right. So this 69% came from the random sample. So that's the sample statistic. %, and then the parameter is P. Well, I guess I should write this. So this is the statistic. This one's the parameter. P, and then in words, we're interested in the percentage of adults who said, or the proportion of all US adults who said they did not want to, or they do not want to see Roe versus Wade overturned. All right. Construct a 95% confidence interval. So you'd look back a couple pages and you'd see that Z star, the critical value, is 1.96. It's about 2, you know, it corresponds to the 68, 95, 99.7 rule. We have the p hat of 0.69 plus or minus 1.96. And now we use p hat times q hat. All over, and the sample size was 1502. Oh, I missed it. There we go. Here we go. Sorry about that. Maybe I'll write the formula to the side again. P hat plus or minus Z star square root of PQ. These are P hat Q hat over N. So don't let the plus or minus freak you out. Just think of one or the other at a time. So the minus one will give us our lower bound because this number will always be positive. The margin of error is always positive. 0.69 minus 1.96 square root 0.69 times 0.31 divided by 1502. And then we also have a plus instead of a minus. And those are our two bounds there. Oh, okay, and yeah, you see how I typed it in. We have a minus and we have a plus. So the interval is 0.667, 0.713. You write it like that. So lower bound, upper bound. So that's not, it's not a coordinate, it's an interval. All right. And I think we can get through 3 and then we can call it a day. And then you guys can study or do your other things. Yeah, relax if you're really stressed out. So now we want to construct a 99% confidence interval. Do you guys think that this will be wider or narrower than the other one, than the 95%? I wasn't able to make anything out. What do you guys think? Raise your hand if you think it'll be narrower. Raise your hand if you think it'll be wider. All right, so to be more confident, we would want a larger interval. Because that would give us a higher confidence level that we actually captured that P. So it's the same, everything's the same, but now we use the other Z, the other critical value. I think it was 2.576, yeah. And now everything else is the same. Can you see that? All right. Over 1502. And then save yourself some time with your calculator skills. I mean, it's not like vital or anything, but it's cool. So you can do second enter, and then you can type over what you had here. 7, insert a 6, like that. The second enter, and you have a minus now. And so it'd be 0.659 and 0.721. 0.659 and 0.721 would be your new confidence interval. The minus is on the left, right there. And then the one where you add is on the right. It's the upper bound. All right, see you guys on Thursday, tomorrow. Yeah.